So, our first speaker is Daniel Kamali from Michigan State University. He's a first-year PhD student. So he will present the work called Neptune, a neuropythonic framework for tunable compositional reasoning on vision language model. Okay, please start.
Okay, thank you, Futa, for your nice introduction. Hello, everyone. I'm Daniel Kamali. As Futa said, I'm a fourth-year PhD student at Michigan State University. I'm working under supervision of Dr. Parisa Korjamshidi. Today, I'm going to talk about compositionality, compositional understanding, and a new neuropythonic framework, sort of a neurosymbolic framework that has been trying to alleviate some of the limitations that are on the symbolic reasoners that are out there right now. So let's just start by understanding what is compositional understanding. So compositional understanding means that you can interpret the complex structures by understanding their parts and the way those parts are combined and how they are connected to each other. Like a very simple example can be thinking about a cheeseburger. Looking at the cheeseburger, you know that this is going to be consist of buns, lettuce, onion, tomato, cheese, and meat. But it's not only important that you know that it's a combined of this part, but the order and the way they are combined is also important. And like when you understand what are the parts and how they're combined, you can see, okay, I have the composition understanding. And we care about compositional understanding because we care about compositional generalization. Because by understanding the parts and the way that they're connected, you should be able to generalize to more complex areas or like more complex scenarios. So some very simple example of compositional understanding is that if you let an AI or a child interact or like observe a set of combination. Let's say we have a yellow rectangle, yellow triangle, and orange rectangle. These are the combinations of yellow triangle and rectangle with one held state for evaluation. When you expose agent with those information, at the time of evaluation, a human can easily understand, even a kid, to, okay, this is an orange triangle, but AI and like agents and all of the models generally fail to recognize a new concept, new composition of the already known concepts. So, and this is gonna fail. But when I'm talking about AI, here I'm talking about like a more general sense of AI. There are different types of AI that you can think about. We have symbolic AI and we have neural AI. In symbolic AI, you have the data, you have the rules, and given the rules, you want to generate some answers based on that. But in the neural regime, you have the data, you have some basic answers for them, and you want your neural method to extract the rules that helps you get the answer in the future steps. So those are two different approach of how to handle, how to have like artificial intelligence. So if you want to compare symbolic and neural method, we have to say that symbolic AI is more data efficient because the rules can be extracted from a set of simple examples, and they are better generalizable because there are set of rules that sometimes are manually generated or like some specific rules are not from the shortcuts in the data, so they can be applied in a more in a higher domain or like it can be generalized. But the main problem of symbolic AI comes from when it goes to linguistic variety. So when you train your model to understand, like when you have a symbolic AI that understands red, but when you get a new word for red, like burgundy, the model doesn't understand what the burgundy means. Like it can fail in that. And the main problem of symbolic is that it's not well applied to real world data. So because and like it's not shown to be as scalable or applicable in real world data, while neural methods have shown to be really good and like they are bypassing all of the benchmarks day by day. So one thing I want to highlight here is that symbolic AI is inherently compositional. It supports compositional understanding. And like with that in mind, something that people want to do is that they want to bring the best of both worlds. They want to have something that is a neurosymbolic AI. It has the neural ability of the model, and it has the symbolic reasoning that is data efficient, generalizable, transparent. And here I'm going to focus on vision language reasoning. So in vision language reasoning, a typical pipeline for neurosymbolic reasoning is going to look like this. You're gonna have an image, you're gonna have a query, you will pass your query to a semantic parser, which is generally going to be an LLM, which is gonna turn that natural language query to a symbolic representation, which then is going to be passed to a grounder, which can be like a VLM, it can be some vision foundation models like GLIP, BLIP, or whatever, or some trained models, trained tools. And then the ground information are going to be passed to a reasoner like problog or some Python execution to get the final answer. And we have many examples of this in the last couple of years. We have ViperGPT, we have Visprog, and we have Left, which are like three of the most famous papers that have been coming out for neurosymbolic reasoning in vision language. Let's look at ViperGPT as an example of what's happening inside of one vision language neurosymbolic reasoning. So this is going to take an image, and for the query, what color do you get if you combine the color of the viper and the flower? So first the model is going to find the object that is viper, then the model is going to find the object that is flower, and then it's going to take the index 0 of whatever object that he has found for viper and flower, and it extracts the colors of both of them and ask another like external LLM, what color do you get if you use the color of flower and the color of viper at the end? But there are some limitations to here. So as you can see, in that step, you were supposed to find the viper exactly where it was. There was no way that if your underlying VLM or VFM has any noise, it doesn't find it with some certain threshold, you will fail eventually because there is no viper to find. So your model is not robust under noise in your grounding. And the other point is, if you want to improve in your domain, or if you want to go to another domain and try to learn new features, these methods need separate data regime for their underlying models. They are not end-to-end differentiable, so you cannot train, like you cannot just give a program that back propagates and gives you some gradients that you can improve your underlying models. So Visprog it's not trainable. It has crisp decisions that are not robust under some noise or some grounding errors. Same goes for Visprog. It's using the same data regime, but just the way that it's implemented is different. It's using the some set of tools. But on the other hand, compared to this Pythonic method, there is a method left, which instead of making these decisions at like a small level that's saying, okay, this object is a sphere, this object is violet or whatever, it's trying to make a global decision. But there are other limitations here as well. Left is first order logic only. It requires training data, so you cannot just put it out of the box in a task. It requires to be trained on that domain. And the predicate cannot go out of the predicate set that you have already trained on. If you go to a new domain with new words or like new concepts, even if they are like similar, your model is going to fail to understand or capture those meanings. So to summarize these challenges, the first challenge was the limited set of predefined concepts. So the model should be able to generalize to whatever concept it wants. The second one is that the crisp local reasoning is not robust under uncertainty and grounding errors. But when we have global reasoning, you can perform better because you have a more global view of your grounding environment. And some methods are only like FOL. They don't have the expressivity of a Turing complete language like Python. And either they are inference only, like ViperGPT and Visprog, or or the training is essential and required for them to work. So our proposed solution here is based on three key innovations. Our goal here is to use a VLM to extract the concept uncertainty. So with doing that, we're going to alleviate the problem of predicate limitations. by using VLMs with a diverse token set that have been trained on, they should be able to capture every concept and every predicate that we want. Secondly, we're gonna have our hybrid reasoning. And that hybrid reasoning is gonna provide us with both local and global reasoning abilities, which gonna help us to avoid the local reasoning problems that one simple error can just propagate all over your reasoning and just failing. And with the hybrid reasoning, we can have a more expressive reasoning compared to the FOL in left. And our third goal or like innovation is that we're gonna have differentiable composition functions that allow our concept grounding to be tuned under the data. And we call our model Neptune. And if you want to compare Neptune to other neurosymbolic methods that are out there, comparing with vSprite, Viper, GPT, Left, Nessie-Coco, and Naver, we are having a hybrid reasoning. We provide both local and global reasoning. We have a dynamic set of predicates thanks to VLMs for concept extraction. We decompose our queries to predicates as level of class, attribute, relations, and spatial relations. And the source of our predicate is vision language models, which are trainable. So at this point, is there any question about what we are doing and why we are doing it? I just want to be clear on the motivation. Everything's good? Any question? Okay. I take that as there is no question here. So
Yeah,
now that
it's good. Thanks.
now that I assume everyone knows my perfect presentation, I will go to presenting how the Neptune looks like. So as I said, everywhere in a typical neurosymbolic reasoning in vision language, you're gonna have a semantic parser. And here we're gonna have an LLM-based program generator, which takes the query and with an LLM is gonna get converted to a Python program. And this Pythonic program is gonna be executed with our symbolic executor, which grounds all of the information from the image with two atomic query functions called score and query, which just ground whatever we have in the program to the information in the image. And this is an object-centric reasoning. So to extract the objects, we have an object detector, which is gonna find all of the bounding boxes of the object in the image. And we use some declarative and imperative reasoning to do the symbolic execution to get the final answer. Okay, so how do we get the Python programs? We do some few shot query to Pythonic code using the LLM. We just have some examples of how the code should be translated, what are the keywords that we require for our object grounding, and we take the program that we need, which is going to provide us with such a thing for program. And the Pythonic program here in Neptune typically consists of three main parts. First is a concept scoring. At first step, we are trying to ground whatever we can from the environment. So in this question, we are looking for a small sphere. So we ask, is the object in the bounding box a sphere? And we ask if the object in the bounding box is small. And then we ground those concepts to these variables. And the second part is the declarative global reasoning that using some like a differentiable function that we implemented with soft logic, we can extract what is a small sphere from the object as a global view of all of the objects that are both a small and a sphere. And on top of that, we do imperative reasoning with some color, with some like, for to extract the colors, we use a Python set and we do loop, condition, everything, and we can use the imperative reasoning to do meta reasoning over the concepts that we have and find the number of colors. So in the Pythonic symbolic reasoner that we have, we chose Python because it's really easy to generate by LLM. Like it's compared to every other symbolic representation that you can find, this is the easiest to generate by LLM. They have seen almost like most of the GitHubs is now Python code. So it's easy to generate for them. And they provide an abstraction for our declarative reasoning. And they are it's a Turing complete language, so it has the imperative reasoning, and it provides us with things like loop, conditional statement, and lets us to have an expressive program that can express anything as long as it can be ground here. So, okay, so we have the symbolic reasoner. We have those atomic functions or whatever. But how are we going to ground them to the program? So this program that you see, how is it going to be connected to the image? So in order to connect those images, to ground the concepts, we're going to use a VLM. So to label those specific objects with any of the concepts that we have, we're going to use visual prompting. So an example of visual prompting is we have the concept cube, and so we mark an object like we mark all of the object, we iterate through all of the objects. But here, let's say we are focusing on this one. We mark this object with blue, and then we'll see if we can find, is the object in the red bounding box a cube? Sorry, we mark it with red. And then we pass it to a VLM, and we take the probability of yes as the object being a cube. So we just take the probability of yes for the model from the VLM to to ground the concepts to each of the objects in the scene. We use this on an abstraction called a score function, which is going to extract for us relations, attributes, like color, shapes, and spatial and contextual information.
So quick time check. It's soon 15 minutes, so please try to wrap up soon.
Yeah.
Thank you.
I have 30 minutes, right?
Oh,
Including the Q&A.
That's including the Q&A?
Ideally. But we can also blend in
Yeah.
the Q&A.
I try to be faster. Okay. So we do the concept understanding. Rather than grounding, sometimes we want to label or describe the object in the scene. We still use the visual prompting with query object to ground them. And we can ask like, what color is the object that is in the red bounding box? And we understand, okay, like the object in the red bounding box is purple. Like we get some short answer for that. And in order to be able to compose this together with because like there should be some first order logic that is like declarative and differentiable, we have some differentiable surrogates that we have implemented. For instance, instead of taking an and, we are using minimum function. That's going to represent the and of like two concepts like red and blue for object, or like multiplication, or like there are different methods that can be implemented for this differentiable implementation. So in order to understand how good is our model, how good are our baseline models, or like we use any VLM underlying with the anatomic understanding, we use the scene graphs from Clever GQA, and we generated some templates with some is the object in a red bounding box, has a relation with the object in the green bounding box, and like is the object in a bounding box a concept? Is it blue? Is it cube or whatever? And we evaluated, with a fun score, we evaluated VLM such as InterVL, CoinVL, and like Ovis in these data sets with the benchmark that we made. So we got, and our results show that the InterVL is the best at like the Clever data set. It gets like 0.94 F1 score, but Quen is the worst at like 86%. But interestingly, in the real world images that come from visual genome scene graphs, QuantVL is the best with like 90% accuracy, like 0.9 F1 score, and OVC is the worst at grounding the concepts in the real world images. So,
quickly in the previous slide, which one is your result again?
no, these are just benchmarking the concept understanding of the VLMs. Because
Okay,
like we're going to use the VLMs, our concept grounder, we wanted to see how good they are. Is their performance adequate or acceptable to be used as a tool?
Thanks.
So when we use our neurosymbolic method, Neptune, on Clever on like 2000 samples. And this is an example of Clever. It has what is the shape of this object that is the largest cube. What shape is reflecting in the largest cube? So it's going to be this small cylinder that is here. So after evaluation on the Clever, we noticed we observed that we get really good performance compared to our backbone VLM. We get like an average of all of the subtasks, around 2%. And most of our improvement comes in counting and comparing numbers, which is like a really compositional task, and it's really hard for the VLMs to do. But on the other hand, we failed at comparing attributes query types, which ask like, is there a blue box that is the same color or same shape or the same texture as like another object, like some other object with some certain properties. So we wanted to investigate what happens in the model that is failing in comparing attributes. So, and especially like the model that is failing, we noticed that Quen specifically is like performing really bad at this data set. And we noticed that analogical concepts such as same size and same shape are really hard for the model to capture in this data set. And it's like the above the worst performing aspect of it. So we wanted to expand our evaluation beyond like just synthetic data and synthetic text. We went to Clever Human, which is like hard, complex human-generated queries. And in that data set, we compared to other methods, Neptune surpassed end-to-end models, the backbone VLMs, and the MDTR end-to-end method. We get like 87% accuracy. They get like 81 and 85. And we surpass other symbolic methods like Left and Nessie-Coco, which are trained on this data set, and the Viper GPT, which is like zero shot. And we are doing all of this at zero shot performance. And on top of that, there are some more complex tasks such as referral expression, visual puzzles, and Raven progressive matrices, which are presented in the left paper. We evaluated our method on those as well, and we showed that we are getting much higher performance compared to zero-shot methods. Viper GPT and VSprog, we are getting much better performance compared to our backbones, and we are just a little bit falling short compared to the trained symbolic methods such as Nessie-Coco and Left. And so we wanted to expand our data set to real images. We wanted to see what happens if we go to real data set, which is real image. We used the referring expression data set. We use a RefCoco adversarial, which is like a complex referral expression task. And like it's trying to make, the goal of the data set was to make it harder for the model to not use the biases that in the training data of RefCoco when evaluating the grounding. And our evaluation in that data set showed that we are outperforming all of the neurosymbolic execution methods. So comparing to Viper GPT, Naver, Neptune is performing like 63% with, and like in this comparison, we are using the same VLM backbone in Naver and Neptune. So we have a fair comparison. And if we are using interVL 2, but if you use interVL 2.5, we even go higher and we can just outperform all of the backbones. We get around like 71%. But that's still not enough to overcome all of the biases in the data. So with some verification step for the decision of the model based on the backbone or uncertainty, we can surpass the backbone and get like 78%, which is higher than all of the backbones that exist. But an interesting observation that we had was that what happens if there is a distribution shift from the data that the model is trained on, but the data that is being evaluated on? So there's a data set called RefGTA. This is a referring expression on Grand Theft Auto game. It's just simulation, and we evaluated our method on that. Our first interesting observation was that our VLMs, which are supposed to be really good at grounding in the previous task, are dropping hugely here. So they go from like 70, 80% performance to 2.75 and like 6.95%. It is like the for the accurate grounding, but Neptune is keeping the high performance. It's performing like 69%, but Viper GPT fails and Naver gets like 54% accuracy in that. And this is an example of the RefGTA dataset. The green boxes are the boxes that are grounded with grounding dyno, and the blue is selected by the VLM. So as you can see, we decompose the query of the man wearing a black suit to just wearing a man, and the man is wearing a black suit, and we compose it with some differentiable function, and we get the best possible object with the global reasoning. And we can see the VLM is giving like while close a wrong bounding box for the grounding. And another experiment that we tried was domain adaptability. Our model showed that what if you want to have a new domain that's like FGTA, but you want to train your model on it? With training on 1,000 samples, we show that we can get from 34% to 69%, but training the VLM with that same set of data only takes you to 32%. Which shows that our method is more data efficient, and with like a 1 billion model that is fine-tuned with this with like a small amount of data, it can even reach the performance of a 8 billion model as a backbone. On top of that, we did some ablation study to show which part we have the declarative reasoning, we have the VLM on each of those. We show that just adding the VLM to a declarative model increases the performance by 12%, but having the imperative reasoning can further boost it to 19% with like 90% to get to like 87.67. And we said Python is easier for the models to generate, and we wanted to have some proofs for that. So we did some evaluation of the program's execution success in like the famous neurosymbolic methods, Neptune, NSTCOCO, Left, HyperGPT, and Neighbor, on Ref Adversarial and Clever. And we can observe that the Pythonic method like Neptune and HyperGPT have a much higher success rate in execution compared to other methods that have their own specific language, like Naver is using Problog, NSTCOCO and Left have their own specific language as well. And we wanted to see if different VLMs make any difference. And we did some evaluation. We tried all of our tasks with InterVL, OVS, and QuantVL. And we observed that we have at least 22% improvement on average across all of the benchmarks that we see. So in conclusion, our hybrid neurosymbolic reasoning works in practice robustly, even in distribution shift. Python execution makes the system usable by coding LLMs. Soft logic let us reason with brittle thresholds. The global reasoning is helping us to avoid all of the execution errors and make the more holistic view of the reasoning. And we show a strong generalization that comes from the separation of the logic and the grounding, which is happening in our method. And our analysis showed that there is still room for improvement, even for atomic relation understanding and grounding in the vision language reasoning. And thanks for your attention. There is a QR code for the paper. I hope I didn't take too much time. I thought it's like 30 minutes for the whole presentation.
Yes, thank you so much for a great presentation. So we have a few minutes for Q&A session, like 3, 4 minutes, 5 minutes. But yeah, if anyone has any question, please raise your hand or just open up. Yep. Anyone?
I might be having a question actually.
Oh,
Yep.
hello.
Hi.
Hey.
So actually, like you have this, so LLM generate the program. So and how reliable that the generated program is, and then you also have this symbolic executor. So does it run the program, or how it basically interpreted it?
So the symbolic executor is just the Python interpreter. So it just runs the program. But because it uses our own implementation of or and like those FOL, it's just some different interfaces that are implemented with some abstraction. And for the program quality generation, there is no direct, we don't have any direct proof that our program the program is correct. But something that the only thing we could show that is that our programs that at least run compared to other methods. Like most of the other neurosymbolic methods have the symbolic reasoning, but they have a fallback of whatever like grounder that they have, or like whatever method that is on the backbone. But for us, our quality which we get is coming only mostly from the symbolic reasoner. It doesn't come from like we fell and we just go on the backbone and we just give you some answer.
Mm-hmm. So essentially, you checked so like all your programs that you generate can run?
I have some analysis on like what happened in the data, like what went wrong. Like something that happened commonly in the LLM generation was that the LLM kept referring with green bounding boxes instead of the red bounding boxes when it was referring to the visual prompt. But that could be easily caught by our regex check. So, but there were some cases in the clever humans, which is a really complex, because like that's human questions and they can be complex and intentionally hard. So some of those could be hard for the model to represent. And I have some examples in the paper in the qualitative analysis part, which you can refer you to.
Mm-hmm. Thanks.
May I have a question?
Sure.
So I'm interested in the inference cost of the method. So, for example, can you control the inference time for each task? For example, if there's hundreds of objects in the image, what happens, or how to control it?
Yeah. Definitely the number of objects is gonna affect the computation size for us. And that's gonna happen like regardless. But there are some methods that we can use for pruning the number of objects of interest. So something that we do is that like when there are like 200 objects in the scene, when we are getting the program from the LLM, we are asking it to give us the keywords of objects that are related. So instead of looking for all of the objects, we are only looking the keywords that we can get or filter by grounding dyno. Like it's not that our model is incapable of reasoning over all of the objects. That's just the efficiency trick that we use to get only the related objects for our reasoning.
Thank you.
And also,
Any other?
like just to say, like I have some evaluation on the time cost, and it takes on like on the I think on the ref code on ref adversarial data set, it takes like 1 second, like 1.2 second for each of the samples. So it's not that slow for this execution.
Thank you so much.
Mm.
Any other questions?
I guess we have to move on, actually.
Okay.
Let me stop sharing then.
And Danielle, could you kind of take over the moderation?
For sure. Yeah. Just let me second. Okay. Hello, everyone. Hello again. We have Futa here to present for us. And Futa is a PhD student from Information Science and Technology at University of Tokyo. And his work is mostly focused on robustness and reliability of deep learning models. I think I was really interested in the paper that I was reading from him on robustness and adversarial stuff. So please go ahead and enlighten us with your knowledge.
Okay, thank you so much for your introduction. So, yeah, I am a PhD student at the University of Tokyo, focused on adversarial robustness things. And this paper, Quality Text Robust Vision, was presented at ICM Multimedia, which was like 2 weeks ago at Ireland. And this would be about it. Okay, and the key idea is robustifying vision language models, but we want to use language information to enhance visual robustness. Okay. So first, let me explain some backgrounds about CLIP. Probably a lot of people already know, but CLIP is a method that learns a shared representation space between images and text and by performing contrastive learning on large-scale image text pairs. And by aligning these two modalities, in the shared space, CLIP enables the zero-shot image classification. So specifically, when an image is input, the model first generates image embedding, and then which is then compared with pre-computed text embeddings to perform arbitrary classification tasks. For example, if you want to do 10 class classification task, we prepare for like
Could we
10
see
prompts.
anything on the screen? Because I cannot see anything on the screen.
Me neither.
Oh, sorry. Wait a second.
Maybe it stopped.
Mm,
Oh, that
Now I can see
is
something.
fine.
do you see it now?
Yes.
Yes.
Oh, I don't know what happens. Okay. So Clip enables zero-shot image recognition. And to do like, it can do zero-shot means you can prepare for arbitrary class. For example, a photo of a cat, a photo of a dog. You can prepare for arbitrary number of classes, and then you compare with, in the test time, you compare image embedding with those text classes and get the closest class in the shared embedding space. So this is very useful, but this clip is, yes, of course, vulnerable to adversarial attacks. So adversarial attacks is like you have image, and then there could be malicious someone could put a imperceptible noise on image, and then clip is easily fooled. So this is a significant risk in real applications of clip. So we need to robustify clip. And the idea came from ICLR 2023 paper is robust clip fine-tuning. So the basic idea of robustifying a model is adversarial training, which is, to explain in a very simple way, you augment data with adversarial examples. So you first generate adversarial examples, and then model is trained on those adversarial examples to correctly recognize them. So this is a very basic idea of robust fine-tuning. And in the context of adversarial fine-tuning of CLIP, this is basically done by robustly fine-tuning on, for example, ImageNet, one dataset. And then since CLIP is capable of zero-shot zero-shot inference, we evaluate on, evaluate on diverse zero-shot datasets. So while trained on ImageNet images or labels, it is evaluated on, for example, CIFAR, or also there are other fine-grained datasets such as food classification, pet classification, flower classification, and so on. So this is a scenario, what we want to do. We fine-tune on some data and evaluate on zero-shot datasets. And this is quite fast, like these methods are only tuned for like 2 epochs, and which takes 2-3 hours if it's a clip base or something like that. So it's quite efficient and also generalizable to other kind of models, but it's mostly focused on clip. Okay, so what kind of baselines are there? So in this concept, there are already various robust fine-tuning methods. So basically, these are like, the questions are how to generate adversarial examples and how to use those to, and how to design the objective functions. And these 3 use only class labels during to generate adversarial examples. And this FAIR method doesn't use any language to generate adversarial examples. So our key question is, can using rich language for supervision improve robustness? So we want to use more language. So here's a quick summary of contribution. So we identified that existing defense methods fail to fully exploit language information to enhance vision robustness. And we propose a QT-AFD. And unlike previous approaches that rely solely on class labels or unsupervised, we leverage rich, detailed image caption to guide adversarial training. And this method achieved state-of-the-art performance in terms of both zero-shot robustness and clean accuracy. So both robustness and maintaining clean accuracy is important. And moreover, we achieve, we do ablation studies of like what kind of language information contributes most and so on. So yeah, let's dig deeper. So we discuss the limitations of existing studies. So we begin with unsupervised adversarial training. And this method doesn't utilize any language information when generating adversarial examples. So in this method, adversarial example is generated to move as far as possible from the original image in feature space. So no using language information. And this adversarial example is used to fine-tune the model. But in this method, this adversarial generation lacks semantic guidance. So there's no guarantee that the adversarial image has deviated from the, for example, semantics of panda or semantics of green, whatever. It just tries to go further from the original image embeddings. So as a result, the robustness achieved in vision language models tend to be suboptimal. And next, there's a supervised method to use class labels. So in this method, adversarial examples are generated to deviate from the class label, for example, a photo of panda. But in this case, the robustness overfits to the class labels. It only cares about class labels. So this image, for example, it's tiny, but there's a panda and there's also like trees, grasses, color tones, spatial layouts. There are many semantics in single image. But when we use only a photo of panda text, it only focuses on class label, the main object. So if we do this, the generalizability is kind of limited. So we want to actually generate adversarial examples that deviates far away from diverse semantics to make model robust to diverse semantics perturbation. Okay. So to address these limitations, we propose QT-AFT, quality text guided adversarial fine-tuning. So the idea is quite simple. We use detailed captions as text supervision during adversarial training. So generating adversarial examples deviates from diverse semantics like bamboo, panda tree, eating green, and so on. And this in turn improves zero-shot robustness, covering diverse semantics. And let us explain details of our method. So first, for each image, we generate a detailed caption in advance using a image captioning model. In our case, intern VL. And then specifically for objective function, we actually combine unsupervised loss to deviate from the original embedding, and also caption guided supervised loss to deviate from diverse semantics. And by optimizing adversarial examples under these two complementary losses, the perturbations are encouraged to move away from variety of semantic concepts. And finally, the model is trained to correctly recognize these caption-guided adversarial examples, enabling it to acquire robustness across a broader range of semantic variations. And this is details of analysis. It's quite a little bit detailed things, but why we combine unsupervised and supervised objectives is explained in this slide. So here we compare the cosine similarity between generated adversarial examples and three reference representations of the clean image, class label, caption. So how adversarial example deviate from these three things. And when generating adversarial example with supervised with a label, we see that yes, indeed, adversarial example deviates from label, but we see that it doesn't deviate much from the original image embedding or captions. So it's kind of too much focus on class labels. And in contrast, unsupervised one, it's quite nice. So it deviates from clean image and also label and caption. So unsupervised one doesn't like overfit to label, but it deviates from diverse semantics somewhat. But this is not enough. And in our ablation study, we find that combining unsupervised and supervised guides the adversarial example pretty much well. So it deviates from like original embedding, but also labels and captions, and this creates kind of strong adversarial examples. So this was a kind of detail, but let's go to the experiment setup. In our experiments, we use CLIP, and training datasets is ImageNet with the synthetic caption generated from image intern VL. And testing datasets is 16 zero-shot datasets. And robustness evaluation is done using
It's not showing
AutoCAD.
anything again if you're.
Oh,
I cannot see anything on the screen again.
do you see it now?
No.
Mm,
Is that an animation or I guess it's
yeah. I am
Oh,
using animation.
I see something here.
yeah, I can see now.
Okay. That's a little bit strange, but now you see experimental setup slide, right? Okay.
We are seeing the result.
We see the results. Yeah.
You see results now.
Yeah, now we
Now
can see
we see the
experimental
set. Yeah.
setup.
Okay. So here is the results. Yeah, please tell me if anything happens wrong again as quick as possible. Okay. So here's the results. So basically our performance, the QT-FT achieves best clean accuracy on average and also best robust accuracy on average. So clean accuracy means when there's no attack, we still want high accuracy. We don't want the trade-off. For example, TECOA, the supervised method, experiences very large trade-off. But our method maintains good clean accuracy, and also robust accuracy is also good. On average, it's good, and we see most data sets, we achieve the best one. And also we did caption quality ablations. So in caption, there are many information, not only object types, but also there are like function words or adjectives. So we were interested in whether those information are important. Are nouns the most important, or are function words most important? And we did ablation study by removing the specific word class. And as a result, we find that actually removing adjectives or removing function words actually degraded the performance. So
You cannot see the results again.
okay. Mm. Do you see it now?
Yes, I see something now.
Okay. Okay. So yes, so in other words, we say the richer and more descriptive caption, the greater its contribution to improve visual robustness in zero-shot settings. And interestingly, when nouns were removed, performance dropped on the object recognition datasets, but the only exception was DTD texture classification datasets. You see the image here now? So DTD dataset has class names of adjective, so like striped or meshed, matted. So in this case, we observed that removing nouns improved the performance. So this finding suggests that semantic guidance during training plays a crucial role in achieving robustness, and task-specific design of linguistic guidance can have an impact on model performance. Okay, let me wrap up. So here's a conclusion. So in conclusion, this study highlighted existing defense methods for visual
No
robustness.
conclusion either.
Okay, maybe animation is not working well.
Yeah, probably.
You see? No?
Not yet.
So, I think it's all right. I mean, it's
Okay.
clear, but
Okay, so yes, we pointed out that existing defenses overlook the usefulness of language in vision robustness, and to address this, we proposed a method which uses rich linguistic information to guide adversarial fine-tuning and achieved good performance on clean and robust accuracy. And yeah, in essence, we introduced a new direction, kind of so enhancing vision robustness by using multimodal nature of vision language models. So this study reveals the crucial role of language in improving visual robustness and contributes to advancing robustness research by introducing a new perspective beyond traditional unimodal paradigm. Okay, thank you so much. Yep, that's all.
Yeah. Thank you, Futa. That was really interesting. The interesting part for me is that the shuffle word didn't like do you remember the hypothesis that was talking about like Eclipse is like bag of word model? And like when I see the performance of the shuffle word, it just further emphasizes that for me that he's still looking at the bunch of word that is there. It doesn't care about maybe the order.
Yeah, Clip definitely cares about the word order to understand semantics. So, but a few percentage decrease, yes. So it's kind of still works if it's completely shuffled. Yeah, that's right.
So maybe I also have a couple of questions or one question. So there are new models, like for example, Tulip, which basically combines also language rewrites, generation of images and text, so multiple objectives, or for example, Siglip, which also performs very well better than Clip already, because it's has like SIGLIP version 2. And now there's also, for example, LaClip, which purely have just language rewrites. Have you tested these models on these adversarial samples or adversarial settings? Because essentially it would basically somehow already incorporate partially what you proposed, and like how are they, like, would be your improvements improve these models as well?
Okay, so those models are just non-defended VLMs, right? As far as I understand. It's just
Oh,
pre-vision language models, or
yes,
is it?
yes.
Okay. So in our experiments, we only focused on CLIP model, and this is definitely a limitation of this work and also the baseline methods. But I think those models, I'm not very sure, but those models share similar objective functions. They should have some image text contrastive learning objectives. So in that case, this method and also baseline methods could be extendable. We generate with similar objective functions. And also using captions could be possible. Probably in adversarial training, when we think of extending to different vision language models, we try to use the original objective functions, but we make it min-max optimization of generating adversarial example with those objectives, and then minimize the objective function while learning the object. Yes. I also have a recent paper trying to extend adversarial fine-tuning on diverse vision language models. If you're interested, please also check my paper. It should be in a Google Scholar or something. Yes.
Okay, thanks.
I have another question. So on the vision language side, vision language model side, I think there are a lot of work on kind of making the model see the difference more clearly, right? For example, there's the binding problem. So there's red cube and blue sphere, for example, and then it does not tell the difference between that sentence and the blue. I forgot what I said at the beginning, but like when the adjectives are kind of swapped and describing a different object, it probably doesn't see the difference. And there's quite a bit of work on trying to make the model understand the difference between these kind of subtle changes. So comparing against this kind of work, I think what you're trying to do is to make the model smoother, in a sense that even if you see just a little bit of difference, the model should still kind of say the same thing. Yeah, so that's what adversarial training is doing. So I wonder whether they actually meet at some point, right? So on the one side, we try to make the model more sensitive. On the other side, we try to make the model more smooth and constant. So can you comment on where we can kind of draw the boundary?
That's a very, very interesting point. I've never thought about it. So yes, definitely, when you just simply make the model smoother, it just becomes smoother. So that we need to think about it. Not, but for example, probably when you make smooth in image classification task, focusing on class labels, simply doing that could deteriorate the sensitivity to those like different words or color attribution, something like that. So in that case, we need to think of the task definition, redesigning objective functions, and that would be much more complex and important things. I think basically, two perspectives: designing data and also how to generate adversarial examples in a semantic direction we want.
Yeah, makes sense. So I guess we need some more kind of fine-grained control over, what the models should see as kind of similar and what the models should still differentiate. It's probably a
Yeah.
very difficult
Mm.
task.
But the syntactic information in like the comparison that you made is different, right? So the syntactic structure of the sentence is still like has the connection of like the blue object and the sphere and red object and like the cube. So the model, if it's trained like it's like the scalability. If you have enough data that is trained, it should be able to have the attention of the based on the order. But otherwise, you need to have some sort of extraction of the concepts or the concept or like the structure of the text to guide you to whatever representation you want. Some inductive bias should play a role there, right?
I agree, yeah. I guess my question is, yeah, realistically, I think it's impossible to cover all these possible combinations and make the model like provide a full kind of exhaustive list of possible changes in the sentence. And so there will be some areas where the model is not covered yet in the training data. In those cases, by promoting the model to be more smooth, do we have kind of adversary effect on these kind of areas where the model was initially kind of being able to differentiate these concepts, but now because the model is more smooth, maybe it loses the ability on this kind of undefined regime?
Yeah, that's a very good point, I think, and that is very possible, I think. So adversarial training usually re should be very specific, kind of. And if you adversarial train in this direction, then other things would be just trade-off, I think, basically. So that's I think a huge limitation of adversarial training methods. Um,
That's interesting. Like I was thinking about it as an out of distribution problem. Like when you're doing this, you are actually if fitting more com or like robustly to your own distribution, right? You're just trying to make your make the distribution more easy for the model to understand on whatever you do the adversarial training. But when you try to do the composition, then you want to go out of your distribution. Then I think those are two different things you are trying to. They're like
mhm,
they're themselves adversarial when you want to think about it.
right. Yeah, very interesting topic. Hmm.
Cool. So I guess the time is up actually. Um, and ideally we wish to wrap this up. So thank you, both of you, for kind of presenting your work.